So, welcome. This is Probability Foundations, EE5110, Probability Foundations for Electrical Engineering. So, this is a postgraduate level course on probability theory. All right. So, this course will essentially, it's a somewhat rigorous treatment of probability theory. I guess you could say it's a more rigorous treatment of probability theory than engineers are normally used to. All right. So, in this course we will take an axiomatic view and focus more on deriving fundamental theorems and proving results rather than more undergraduate like treatments where you are probably the focus is more on solving problems and computing expectations and computing probabilities and so on. So, at that level, so you can think of this course as a more conceptual course. There will be more emphasis on proofs, all right, more emphasis on rigorously deriving things and a greater degree of conceptual understanding. Right. So, this course, so who should take this course? So, if you think about it that way, is it right for you? So, this course is meant for people who are essentially more mathematically minded. So, people who will benefit from it are the ones who will probably do more mathematical research. So, if you are working on topics like I don't know, certain computer networks or stochastic control or machine learning, where you need a somewhat strong foundation, conceptual foundation in probability, this course will be very useful for you. So, this course EE5110 runs in two different avatars. Okay, it's offered in both semesters, both odd and even semesters. It has the same number, but the version that's offered in the even semester is more operational. It's more computational and operational, and there is more emphasis on problem solving. Right. So, if you are a more practical person who has greater use for problem solving and computing things and so on, and not so much, if you are not so interested in really getting into the nuts and bolts of probability theory, maybe the even semester course may be more appropriate for you. So, this is a call that you may want to take, whether you want to take it this semester or during the even semester. It is called the same thing, but so this version will be more theoretical, more conceptual. All right. So, for example, this semester this is the measure theoretic version of the course. Okay, this course will have measure theory in it, and the even semester version, although it's called the same thing, it doesn't have measure theory in it. It's a slightly more elementary treatment conceptually, although there will be more emphasis on problems and computational aspects of probability. All right. So, you may want to decide which one is for you in some sense, right? You can always take this call in a few weeks, I guess. All right. So, so I'm Krishna Jagannathan, Electrical Engineering Department. That's where you can contact me. So, the course has a website. This is, if you go to my web page, you can find the link to this web page. This link right here lists the entire course content. Okay. So, all the topics we will cover are in fact given here. So, I suggest you visit this today. All right. So, reference material. Let me write it down here. So, there is no one book out there which closely follows what we are going to do. Okay. So, there is a number of material that I am going to suggest. So, you do not have to buy all these books. Okay. So, I think the book that you should probably consider seriously buying is Grimmett and Sturzaker. Okay. This is probably most well matched with the kind of this is a very good book. It's a very classic book. So, this is something you may want to consider buying. Sturzaker, 3rd edition, Probability and Random Processes. All right, Oxford University Press. It is an expensive book. Right? It's about 2,800 rupees or so. It is an excellent book though. So, if you at all, this will be a standard reference. And there is another open source reference which I will follow quite a bit. It is MIT OCW, OpenCourseware. There is a link on the home page. All right. So, if you go to the web page, there is a link. So, this is also a very useful source. We will follow certain lectures from there. It's a good source. So, these two are roughly at the level at which we'll be doing this course, and there are other textbooks which are either slightly at a more elementary level or at a more advanced level, right. So, I will list a couple of them also. So, there is a book by Bertrand and Paradox. This is slightly more UG level. Okay. It's an excellent book, Bertrand and Paradox Introduction to Probability. And there is David Williams, Probability with Martingales. Okay, this is a beautiful book, but it's more advanced than what we will need, what we will cover. But there are certain topics here which are just beautiful, right? So this is this one, and there's one by Rosenthal. These two books are more advanced. David Williams and Rosenthal, they are both more advanced than what we will cover, but there may be few results and few things that I may refer to these books. But in any case, both these books are beautifully written, very, very good books in more advanced probability theory. There has been, so this is what, so roughly this is really what mostly you need to focus on, right. These two references are enough, I think, and these are occasionally, I think, will be occasionally useful. There is also an effort going on by students from the previous years to actually LaTeX the notes from previous years of this class. So that, I mean, just as I mentioned, there is no one book that covers all the material in one place. So we figured that it may be a good idea to just put everything down on LaTeX. So students from previous years have actually collaborated and formed a group to LaTeX the notes from previous years. Okay, so those notes are the first round of the editing is over, and so I will make them available to you. All right, so I will put them. So the class notes, LaTeX. Let me write it this way: LaTeX class notes. To be uploaded periodically on Moodle. Okay, so these notes will be uploaded from time to time. So the thing is, these notes are, I think they are all right. I think they are not yet fully polished. So you have to realize that they are just coming out of the press. So there may be some minor errors and they may not be very polished. So I will give them to you, but just remember the caveat that there may be the occasional mistake, or there may be some errors or bugs or typos in there. If you find any bugs or errors or typos, please let us know. So that the idea is to improve these notes as we go along. Right? It's like a collaborative effort to get it done. So we will build up from basics. Okay, so there is nothing that I'm going to really assume other than some basic real analysis concepts. So we will really be starting from the very basic stuff. Okay, I will start. If the real course material I will start on for the next from the next lecture. Today I just want to get some sense from you on what you think, why we study probability, and what it is that probability theory does. Why are we interested in it? Right, so can I get some your feelers from you on why you think, what is probability theory and why people study it? So to study non-deterministic events, right? So is that a convincing answer for you?
It's a mathematical approach to study experiments with uncertain outcomes.
Mathematical tools to study experiments with uncertain outcomes, right? So it's basically what it is. So if you want a very concise way of looking at it, probability theory is it essentially is the science behind randomness, right? It's the science of randomness, right? So there are in real life we know that there are so many events that we encounter which we don't seem to have a perfect control over or perfect ability to predict or a perfect knowledge of, right? Things such as the toss of a coin or toss of a die, or what the weather is going to be tomorrow, or whether whether a child is going to be a male or female, right? These are things that we don't seem to have control over, right? Or we don't seem to have a complete understanding over. And so these are, but if you, the thing about these random events, so called these random or non-deterministic events, is that there is a larger pattern to them. right? That is the central point, right? Although apparently the one time I toss a coin, I have no idea whether it's going to be head or tails, or I have no idea whether I really can tell the temperature tomorrow. There is a larger pattern to these things, right? So you know, for example, that although you don't know the sex of the baby that's going to be born, on an average half of them are men and half of them are women, right? So or roughly if you toss a coin a million times, roughly half of them turn out to be heads, right? So these are certain large scale patterns, or long term certain patterns, or what may be called, I guess patterns is the right word, right? So patterns that one observes in these seemingly random events, right? And probability theory tries to quantify these aspects, right? It's a theory that helps us to mathematically capture the pattern behind these seemingly random events, right? That's really what probability theory does. Now these games of chance have been played even since the ancient civilization. So it's been around for a long time, and actually even for the last several centuries, people have been computing odds and winning bets and so on, right? So I guess for a few centuries, people have been computing probabilities at some level or the other, right? Although the mathematical theory of probability, the more rigorous foundations of it were laid only about a century ago. So probability theory as we know it today is only about 100 years old. Okay, it's primarily the primary person, the mathematician who primarily contributed to it, to the modern theory of probability. Do you know? Yes, Laplace made contributions. In fact, Laplace he did make significant contributions that's about 3 centuries ago, I guess. But I said the modern theory of probability is only 100 years old. It's a very famous mathematician, Kolmogorov, right? A great Russian mathematician by name Andrei Kolmogorov. Right. So he is the father of modern probability theory. So essentially, he cast probability theory as he realized that it's basically a special case of what is known as measure theory, which was developed by 2 French mathematicians primarily, Borel and Lebesgue. Okay. And then of course, last 100 years there has been an explosive development of this probability theory. So what we will do is in fact this axiomatic modern probability axiomatic approach. So the question arises, why do we need it? So even well before Kolmogorov, people have been computing probabilities, right? People have been computing their chance of winning bets, odds of winning bets, and so on, right? So why do we even bother? Why do we need this more sophisticated theory or more rigorous mathematical theory? If you can compute probabilities, you can. That's all we need, right? Practically, that's all we need. If I tell you that probability of a certain event is blah blah blah, you think that, so let's say if the probability of an event is 1 by 3, well, it occurs roughly 1 out of 3 times, right? And we know this is all we really need in practice. See, the reason that there is this, that people have bothered to make this a rigorous mathematical theory is because before Kolmogorov, people have been running into all sorts of paradoxes and contradictions. Because without a proper theory, you run into all sorts of problems, right? Because if you only go by a certain intuitive understanding, you can run into difficulties, right? To illustrate this, to illustrate the importance of an axiomatic theory, right? There are many paradoxes that you can come up with if you're not careful about doing this probability theory in a rigorous way, right? So there are many paradoxes that you can run into. Okay, so what I will do is I will just describe one such paradox to you. Okay, very famous paradox, and that will hopefully send the message across to you on why we need to be a little more careful than just a normal intuitive understanding of probability, right? So this paradox, it's a well-known paradox. So you take a circle, okay, you take a circle and you inscribe a equilateral triangle in it. Okay, let's see, this is the center, So, you have a circle and an inscribed equilateral triangle. Okay. So, let us say this radius is, just 1, okay, it can be r or whatever, 1, okay. And so, if this is 1, then this is also 1, and then this will be, so this side will be square root of 3, right. Side of the triangle will be square root of 3, isn't it. So, the question is the following. So, take a circle and draw a chord uniformly at random. What is the probability that this random chord is longer than square root of 3, which is the side of the inscribed equilateral triangle, right. So, the question is, you basically close your eyes and draw a chord, all right, and the question is, so you draw a chord, okay. So, this is the length of the chord, right. The chord may be like this or chord may be like that, right. So, in this case this will be the length of the chord. So, if you pick a chord uniformly at random, what is the probability that the length of the chord, in this case this or in this case that, is longer than the side of the inscribed equilateral triangle, or what is the probability that this is larger than square root of 3, which is the side of the equilateral triangle, right. So, this is a question, right. So, it turns out that this is okay. The reason this is a paradox is, depending on how you look at it, you get different answers to this question, okay. So, there are in fact there are 3 perfectly reasonable sounding arguments which give you 3 completely different answers, okay. So, the first, so let me see if I remember these correctly. So, the first way of seeing this is, so you want the chord to be longer than this side, right. So, what happens is, so if you draw the incircle of this triangle, so this guy is an equilateral triangle, let us say you draw the incircle of this triangle, okay, and if it so turns out that the chord you draw, let us say you draw a chord, if it so turns out that the midpoint of the chord is inside the incircle, you can show that it will be longer than square root of 3, right. So, in this case, in fact, the center of the chord is inside this incircle, and you can see that this guy is longer than square root of 3, right. Whereas, if it is a chord like that and the midpoint is outside the incircle, it will be shorter than square root of 3, correct. So, so you may argue here that, so in this case, so this is the first possible construction, right. In this case, the probability that your random chord is longer than square root of 3 is simply the probability that the center of the chord falls inside this little circle, incircle, correct. So, you are essentially looking at, so the question you are really looking at is, where is the center of the chord, correct. If it is inside the incircle, you are longer than square root of 3, if it is outside the incircle, it is shorter than square root of 3. So, essentially you are looking at the probability that the center of the chord is inside that incircle, right. Now, you know that the radius of this incircle is how much? This is half, right, because this is the centroid, and so this divides it into 2 to 1. So, this radius is half, right. So, the probability that your center of the chord falls into this circle is how much? If it is uniformly at random, then it should be area of this little circle divided by the total area, right. So, in this so the midpoint of the chord. So, if you take the argument about the midpoint of chord, so the answer you get is 1 by 4. You see why? Because you are looking at the point, the midpoint falling inside the radius of the circle of radius half, whereas the whole radius is 1, right. So, and the area of this is of course 1/4 the area of the bigger circle, right. So, this is one answer, right. So, this is a perfectly reasonable argument, right. The trouble is that, I mean, you will probably say okay, this is the answer and that is it, right. The trouble is that there are also other perfectly reasonable sounding argument which give you other answers, different answers, okay. Yeah, so the second, let us say the second argument goes as follows. Let me erase these. So, let us say that you fix, let us actually get rid of this triangle as well. Okay. Another way to draw a chord uniformly at random is to just fix one end of the chord, all right, wherever you want. Let us say you fix it here, all right, and consider. So, let us say this is the tangent or that point. Okay, this is one end of the chord, and you can draw the chord like that or like that, right. Now, whether or not this chord is longer than square root of 3 or shorter than square root of 3 will depend on. So, here is where, so if I draw an equilateral triangle from that point, it will look like that, right. So, it depends on the angle that this guy makes with the tangent. So, if this chord is making an angle of, so this equilateral triangle makes an angle of 60 degrees, pi over 3, right. If this angle is less than pi on 3, right, I will be shorter. But equivalently, if that angle is greater than 2 pi on 3, right, if it is like that, it will be shorter, right, the chord will be shorter. Whereas, if the angle made with this tangent is between 60 degrees and 120 degrees, pi on 3 and 2 pi on 3, my chord will be longer than the side of the triangle, correct? Make sense? So, essentially what I am doing is fixing one end of the chord, right, and then looking at what angle it makes with the tangent. So, from that point of view, it looks like, so if this angle is uniform, right, because it is a random chord, so it does not prefer any particular direction, right. So, if the angle is uniform, then the probability that you are longer than square root of 3 is simply the probability that this theta is lying between 60 and 120, pi on 3 and 2 pi on 3. What is that probability equal to? 1 by 3, right, because, well, this angle is uniformly at random, chosen uniformly at random. So, if you make this this angle with tangent this argument, you get answer equal to 1 over 3, correct. Already you have two different answers to the what seems like the same question, right. I have just argued it, I have not made any mistakes, right. I am not cheating you with any some simple, this is not any mistake that is going on, right. I have computed it correctly and I am getting two different answers. Actually, there is even one more way of getting a different answer altogether, and that the argument is as follows. So, that is the triangle. So, you take one side of the equilateral triangle, all right, and you draw that perpendicular, okay. So, what you are doing is now you are fixing the, so you are fixing the direction of the chord, all right, and you are just going to move the chord up and down, all right. So, whichever angle you want, you fix the angle of the chord. So, and you are just going to move it up or down, and you are going to draw the equilateral triangle parallel to it, okay. The side of the equilateral triangle will be parallel to it. So, now if you see, if you are only going to draw chords which are parallel to this guy, it does not have to be horizontal, it can be any other direction. I will just I will just rotate the equilateral triangle. So, the fact that this is horizontal is not any big deal. So, you can see that if you draw a chord like that, it will be longer than square root of 3, and if you draw a chord like that, it will be smaller than square root of 3, correct. So, what we are seeing is, so if you take that radius, the probability of the chord being longer than square root of 3 is simply the probability that it is lying above this point. The center of the chord is lying above that point, correct. So, if you are above this point, you are longer, and you are below, you are shorter. So, if you look at this radius, and if you think that if you let us say that the center of the chord is uniformly distributed on this radius, right, then you are looking at, so this is midway, right. So, this is midway between this and this. So, you would conclude that the probability, the required probability is half 1 by 2, right, because this is this in this length you are longer and this length you are shorter, correct. So, in that case you will get, so if you look at, what should we call this, so the distance center of circle and center of chord, right. So, if that distance is uniformly distributed, because it is not, it does not prefer any particular radius, you will get the answer is half, right. So, there, so it is what was posed in English as seemingly well posed question, it has led to 3 perfectly reasonable sounding answers. There is nothing, they have not made any mistakes here, all right. So, there is no cheap error, okay. It is actually a deeper problem going on, okay. Now, the question is what is happening, right. So, there are no paradoxes, right, there are all paradox, I mean if at all you want to be consistent, you have to have a resolution, right. There should not be these kind of paradoxes in any theory you build, right. So, what is the resolution? Do you have any, do you already know, or do you have any guesses? So, the same question, right, I am taking the same English question, right, and in translating it to mathematical languages I have done it in 3 different ways and ended up with 3 different answers, seemingly correct all 3 of them, but the question is the same question, right.
In the sample space we are taking every element in events. In the case 3, the sample space don't have every element in events.
Well, okay. So, I did not quite understand what you said, but I heard the word sample space, right. So, okay. So, that is an important concept, right. Any other guesses?
The first method, actually all the points are not equally likely, right? Like the center point can have n chords, infinite number of chords going through that.
Well,
as
all
you
points
point.
can have infinitely many points, chords going through them.
As you come to the side, like all the there may not be infinite number of chords going.
There are.
Infinite number of chords will be there, but as center point, as that point, it won't be there infinite. No?
That is not true. Right, still each point will have infinitely many possible chords, right. So, that is not the answer either, right. So, there is something, so this is not some cheap error, all right, this is not some little mistake that I have made somewhere. So, it is actually an intriguing question, why this is happening, right. It is actually a slightly non-trivial explanation. So, the one word I heard is this about sample space, which is a very important concept that we will study. So, to state it in plain English, we are getting 3 different answers because we are answering actually 3 different mathematical questions. Okay, so, what I posed as a plain English question, which I wrote as random chord within quotes, right. So, we are getting 3 different answers because we are actually, they are answers to 3 different mathematical questions. Okay, So, if the questions are different, the answers can be different, right. It seems like they are the same English question, but mathematically actually they are answers to 3 different questions. In more formal terms, the sample spaces, the probability spaces involved are in fact very different in the 3 cases. Okay, I will of course define these terms more carefully as we go along, but in this case the midpoint of the chord being within the circle, there the sample space, we are looking at the center of the chord, and the sample space we are looking at is the whole circle, and we are looking at a uniform distribution of the center of the chord within the circle. Similarly, in the second case we are looking at the uniform distribution of the angle that it makes, right. So, although it seems like they are all uniformly drawn chords, mathematically we have solved 3 different mathematical problems. So, the mathematical questions and the probability spaces, the sample space behind each of them are in fact different. Okay, they are not the same, it is not the same problem, we are getting 3 different answers because we are answering 3 different questions in mathematical terms. Okay. Is that okay? So, which is why we are getting 3 different answers. So, it is actually not what seems like the same English question are different mathematical questions corresponding to 3 different sample spaces, therefore, you get 3 different answers. Okay. So, which is why so why did I give this example? Just to warn you or give you a caveat that if you are generally loose about these things, so if you generally say a random chord without really mentioning what the sample space is or what the underlying probability space is, you can get into all sorts of confusions. You can get any of these 3 answers. Maybe there are more answers you can get if you if you pose some other problem, you get a different answer, right. So, I hope this has kind of slightly opened your eyes at least to the possibility that you have to be a bit more careful in talking about things like a random point or a random chord, or these things you cannot be very loose about, you have to specify in a more precise way. So, the 3 different questions are, so we will do this, we can once we do all these sample spaces and stuff, we will become more clear. So, in this case, as I said, you are considering the distribution of a midpoint, your distribution of points inside the circle uniformly, and you are looking at the probability that the midpoint of the chord lying inside the circle. So, it is like, so the sample space is the entire circle itself, and it is a uniform distribution inside the circle, and you are looking at the center of the point being inside the smaller circle. Whereas, for the second case, for example, the sample space is this theta, right. I mean the set of the thing what you are varying is theta, it is not the center of the chord. So, it is finally, so the sample space is between 0 and 2 pi, and you have a uniform distribution in that. So, they are all different mathematical questions, it is not the same question, it seems like the same question in English, but not in mathematical terms, right. In the second, so in the final case, for example, your sample space is 0 1, interval 0 1, where you are putting the chord, right. So, they are actually different probability spaces, different sample spaces, and therefore, different mathematical questions. Okay. So, you can learn, so this is called Bertrand's paradox. So, actually Wikipedia has a good article on this, and the book by Ross also has this, I think. You can, they have even simulated all 3 of this and shown what the chords look like. Okay, so, this is a pretty interesting article to read. Okay, this is a very famous paradox in probability. I will point out a few more paradoxes as we go along. Okay, there are some interesting paradoxes you can cook up. There is another paradox in probability theory on why you need a measure theoretic view of probability, that also I will point out later. Okay. This is just saying that you have to be careful defining sample spaces, defining what your underlying probability space is and so on.